EE World, I'm Martin Rowe. We are at the Brooklyn 6G Summit at the NYU Tandon School of Engineering, and we have a demonstration here that I'd like you to hear about. And we have Ishaan over here, and this is for channel sounding. You can see there's some antennas in the background, and Isha and Ishaan are going to explain about how this system works. This is part of their research. So Ishaan, why don't you start?
Thanks. So this is our channel sounder. We use it to characterize channel qualities, and so when we open up new bandwidth areas, what that allows us to do is get a nice clear picture of what the channel looks like, and we get a bunch of characteristics such as delay spread, received power, path loss exponent, and it really gives us a nice picture of the channel. So what we have here is the transmitter and the receiver. And so as you can see right now, they're in non-line of sight configuration. The other configuration is line of sight, where the two antennas are facing each other. But in this case, the two antennas are pointed towards that wall. And so what happens is that the signal that gets transmitted from that antenna bounces off the wall and comes back to the receiver, where we can see this power delay profile over here. So how we do this is we use a pseudo-random noise sequence. What that is it's essentially a function. It's a semi-random function, meaning it's fully deterministic once you select the function, but different functions will produce different results. So what we do is we generate a pseudo-random noise sequence at the transmitter end. We up-convert it to the frequency that we're trying to measure. We transmit it. In this case, it's going to bounce off the wall and get captured by the receiver. And at the receiver end, we generate that same signal using the same pseudo-random noise sequence at a slightly slower clock speed. And what that allows us to do is get a time-dilated power delay profile, meaning it gets slightly stretched, and that allows us to get a much clearer view of the channel. And all this essentially contributes to opening up new bandwidth, as things that have not been seen before are now able to be seen, and with the gold standard of data.
What's the frequency that you're transmitting at?
Well, right now this is they did FR3 measurements last year, so 6.75 gigahertz and 16.95 gigahertz. But they're in the 7 gigahertz and 17 gigahertz bands.
Okay, thank you. And Isha, why don't you tell us a little bit about what you do with all this data?
Yes. So with all the measurement campaigns and the measurement data we collect through the whole campaign, we put the measurement data in our open source NYU Sim MATLAB based simulator. NYU Sim is a channel simulator which is based on real world measurements data. We generate channel impulse responses in NYU Sim, and you can see that in NYU Sim we have also the 3D antenna patterns. We can actually show you the simulation, how it works. It's on that PC. Yes. So this is the GUI for NYU Sim. You can see we can adjust the frequency, bandwidth, environment, and a lot of different parameters such as antenna properties, antenna distance, and everything. We also have human blockage parameters in display, and also spatial consistency is considered in the environment. Can you play? We also will simulate this, show you live what kind of channel impulse response this generates. So this is the directional power delay profile that we have on the screen here.
Okay.
Which is helpful for us to examine the multipaths that we see. This is the omnidirectional PDP profiles at 28 gigahertz. This is the user track. So when the user moves, it does not change abruptly. It does like a smooth transition. This is the line of sight and non-line of sight condition map around the user. So this is for the line of sight condition we have. And this is the spatial shadow fading map. So this spatial consistency mode allows us to see the user change. When the user moves, the track moves smoothly along with it, and there are no channel impulse responses that are abrupt.
Okay, thank you very much.
So much.